Welcome to this video about how to use LDA as a classifier. In this video, we'll briefly discuss how LDA combines variables. Watch the lecture about the basics of LDA to get a deeper understanding of how LDA is computed. Next, we'll see how we can find an appropriate cutoff value based on the discriminant scores, and how to calculate the sensitivity and specificity and learn how to generate an RC curve. We then briefly discuss how we can validate the LDA and how to use LDA to classify with more than two groups. Remember from the basic lecture about the LDA that the LDA is a method that aims to maximize the separation between two or more groups. The method combines variables so that the linear combination has a maximal separation between the groups. To achieve maximal separation, it finds optimal values of these weights. LDA will put more weight on the variables that are good in separating the groups. To show how LDA can be used as a classifier, let's have a look at the following fictive dataset, which contains information on 12 patients. This is the same dataset as we used in the basic lecture about the LDA. The blood concentration of the C-reactive protein as well as the body temperature have been measured on 12 patients that have entered the hospital. Once the patients had entered the hospital, the presence of bacteria and viruses were analyzed from different samples. However, it usually takes several hours or days to determine if the patient has a viral infection or a bacterial infection. After 2 days at the hospital, these 6 patients were found to be infected by a virus, whereas these 6 patients were confirmed to have a bacterial infection. Since antibiotics are only effective on bacteria, only these patients were treated with antibiotics. The problem is that we have to wait about 2 days to confirm the type of pathogen. We therefore need to wait 2 days to know if antibiotic treatment is appropriate or not. It would therefore be great if we could use the CRP concentration or the body temperature to tell if the patient has a bacterial or viral infection, because the measurements of these variables can be done within just an hour. If we plot the CRP concentration of the 12 patients, we see that no simple cutoff line can be used to separate the ones with a bacterial infection from the ones with a viral infection. The same is also true for the body temperature, because we cannot separate the patients with a bacterial infection from the patients with a viral infection by using only the body temperature. However, if we plot the CRP concentration and the body temperature in the same plot, and use different colors for patients with a viral infection and bacterial infection, we can see that the following line can separate the two groups completely. This indicates that LDA would do a good job in separating the groups by combining the two variables. Just as PCA, LDA can be seen as we rotate the data into two new dimensions, which are here called discriminant function 1 and 2. We can see that the first discriminant function can be used to separate the two groups perfectly. In contrast, we cannot separate the groups based on a horizontal line, which means that the second discriminant function is not useful for separation. We can therefore delete the second discriminant function and place all data points on just one line. For illustrative purposes, we here rotate the plot so that the data points are plotted vertically. If we use LDA, we can plot the so-called discriminant scores like this. We can now place a cutoff value like this one that gives us a perfect separation between the two groups. By using LDA, we have combined the two variables CRP and body temperature in a way that has maximized the separation between the two groups. The linear discriminant scores that you see in this plot can be obtained by the following equation. We can replace x1 and x2 with the variable names CRP and temp. The values of our weights, alpha 1 and alpha 2, were computed with the statistical software to 0.11 and 0.7. These values give us the optimal separation between the groups. Watch the previous lecture about the LDA to see how these weights are calculated. Let's use this equation to calculate the discriminant scores. If you plug in the CRP value and the body temperature for the first person in this equation, we see that the corresponding discriminant score is calculated to about 29.5. The following point represents this score. We use the same equation to calculate the scores for the other individuals as well. We can see that the scores for the ones with a viral infection are lower compared to the ones who have a bacterial infection. One way to find a good cutoff value is to calculate the means of the discriminant scores of each group. We see that the mean discriminant score of the viral group is 28.9 and 32.3 for the bacterial group. The mean of these two means is about 30.6. We can see that 30.6 is a good cutoff value to use, since it separates the two groups completely. However, it is common to center the discriminant scores by first subtracting the means from the original values. By using this equation, the following sentence scores were calculated. To get this value, we multiply this weight by the difference between the original CRP value and the mean of the CRP variable, and add to the weight 0.7 times the difference between the body temperature of the first person and the mean body temperature of all individuals. We can also calculate the sentence scores by subtracting the mean of the discriminant scores from the original scores. If we plot the centered scores, we see that the scores center around 0, since the mean of these scores is equal to 0. The means of these centered scores for the two groups are minus 1.71 and 1.71. The mean of these two means is equal to 0. A reasonable cutoff value based on the centered scores in this case is therefore 0. We'll now see how we can calculate the sensitivity and specificity based on the predictions by the LDA model. Note that we'll here use our original scores to predict if a person has a bacterial or viral infection. We will use the cutoff 30.6, which is the mean of the two means. A person with a discriminant score greater than 30.6 will be predicted to have a bacterial infection, whereas a person with a discriminant score less than 30.6 will be predicted to have a viral infection. Let's add an additional column in this table that shows the predicted class based on the LDA function. Since the discriminant scores for these 6 individuals are less than 30.6, LDA predicts that these individuals have a viral infection. And since these discriminant scores are greater than 30.6, LDA predicts that these individuals have a bacterial infection. We see that all individuals with a viral infection are correctly predicted by LDA to have a viral infection. We also see that all individuals with a bacterial infection are correctly predicted to be infected by bacteria. Let's decide that a bacterial infection is associated with a positive test result, whereas a viral infection is associated with a negative test result. Note that the selection in this case is arbitrary in this example, since we do not have disease versus healthy. Since the bacterial infection is associated with a positive test result, we here have 6 true positives and no false negatives. Remember that the sensitivity is how often the test shows a positive result out of the ones who have the disease, which is here defined as having a bacterial infection. Since all patients with a bacterial infection are correctly predicted, the sensitivity in this example is 100%. Remember that the specificity is how often the test shows a negative test result out of the ones who would not have the disease, which in this example represents the ones with a viral infection. Since all patients with a viral infection are correctly predicted, we have 6 true negatives and no false positives, which result in a specificity of 100%. We can also calculate the accuracy. Since all patients are correctly predicted, the accuracy is therefore 100%. Watch the lecture about sensitivity and specificity for a deeper explanation of these metrics. Note that we can change the cutoff value depending on if we think that the sensitivity is more important than the specificity. Watch the lecture about RC curves for more information. If you, for example, like to be more certain to actually detect all bacterial infections for future data, we could use a lower cutoff value. By using a cutoff value of, for example, 29, we'll be more confident that we actually identified all patients with bacterial infections and treat these with antibiotics. However, this means that some patients with a viral infection will also be predicted to have a bacterial infection and will therefore incorrectly be treated with antibiotics. We'll now see how we can create an RC curve based on the discriminant scores. By using a very low cutoff value, all individuals will be predicted to have a bacterial infection since all have a discriminant score greater than the cutoff value. This will result in 100% sensitivity and 0% specificity. If we increase the cutoff value to 28, one of the individuals infected by a virus is now correctly predicted to have a viral infection, which increases the specificity from 0% to about 17%. If we continue to increase the cutoff value, 2 of the individuals infected by a virus are now correctly predicted to have a viral infection, which increases the specificity from 17% to about 33%. And if we increase the cutoff value a bit more, the specificity is increased to 50%, 67%, 83%, and finally to 100%. At this cutoff value, we get a complete separation between the groups, which gives 100% sensitivity and 100% specificity. If we continue to increase the cutoff value, the sensitivity is now reduced from 100% to 83%. If we test all possible cutoff values, we can generate the full ROC curve. Note that since we in this example have a complete separation between the groups, the area under the ROC curve is equal to 1. We'll now see how we can compute probabilities based on the discriminant scores. The following probabilities were calculated for this example data. These probabilities represent the probability of having a bacterial infection because we previously decided that the bacterial infection was associated with a positive test result. These probabilities can be computed by assuming that the scores are normally distributed. The shape and the location of these 2 normal distribution curves are based on the pooled standard deviation and the mean scores of the 2 groups. The curve for the viral group has a mean of 28.9, whereas the curve for the bacterial group has a mean of 32.3. These probabilities have been computed based on the heights of the 2 curves. For example, a score of 30.8 results in a probability of 69.5% that this data point is of class bacteria. This probability is calculated based on the height of the curve for the bacteria group, which is 0.132 for a discriminant score of 30.8, and the height of the curve for the viral group, which is 0.062 for the same discriminant score. The height of the bacteria curve is about 68% out of the total height of the two curves. This is how this probability value is calculated. Due to rounding effects, we do not get the exact value as in this table. The importance is to get an idea of how the probabilities are calculated. These probabilities can be adjusted based on the prior probability, as we discussed in the video about the positive and negative predictive values. For example, if viral infections are more common than bacterial infections, these probabilities can be adjusted based on such prior knowledge. By using these probabilities, we can for example say that the probability value less than 0.5 should result in that we classify the patient as having a viral infection, whereas the probability greater than 0.5 should be classified as a bacterial infection. Since these probabilities are less than 0.5, we predict that these persons have a viral infection. And since these probabilities are greater than 0.5, we predict that these persons have a bacterial infection. We'll now briefly discuss how we can validate our model. Watch the lecture about validation to learn more about different types of validation techniques. To validate the LDA, we could split the data into a training dataset and a test dataset. We then use the training data to compute the linear discriminant function. We then determine an appropriate cutoff value. Next, we remove the training data and use the test data to calculate the discriminant scores with the weights that were estimated based on the training data. We then use these discriminant scores to compute metrics such as the sensitivity, specificity, and accuracy by using the given cutoff value we decided based on the training data. Once we have validated the model and decided on an appropriate cutoff value, we could use the model to make predictions. In our example, we use a cutoff value of 30.6. For example, if a person has a CRP value of 45 and a body temperature of 38, we can predict the class based on our discriminant function. We see that the discriminant score is 30.5, which is greater than a cutoff value 30.6. We would therefore predict that the person has a bacterial infection given our simple example with fictive data. Based on the heights of the two normal distribution curves at the value 30.5, we can compute the probability for a bacterial infection to 95%. In comparison to, for example, logistic regression, LDA can be used with more than two groups. We'll here see how we can use LDA to discriminate between three species in the classical iris flower dataset. This dataset consists of measurements of the sepal length, sepal width, petal length, and petal width. These four variables were measured on 50 setosas, 50 versicolors, and 50 virginicas. The iris dataset looks like this. In total, we have 150 rows, where each row represents the measurements of one iris flower. These columns show the sepal length and width, as well as the petal length and width in centimeters of the first 19 flowers in the iris dataset. The last column shows the three species, Setosa, versicolor and virginica. We see that the first 19 iris flowers are of species Setosa. By using a statistical software, the following weights were computed for the first discriminant function, which generates a maximum separation between the three groups based on the sepal length, sepal width, petal length, and petal width. If we plot the discriminant scores of the first discriminant function for the 150 flowers, we see that the Setosa flowers separate well from the other two species, whereas there is some overlap in the scores between versicolor and virginica. If we use the following cutoff values based on the average of the means of the neighboring groups, then we see that all Setosa and virginica flowers are correctly classified, whereas two versicolors are predicted as virginicas. Since we made 148 correct predictions out of 150, the accuracy of our classifier is 98.7%. We can now use our linear discriminant function to make predictions. Suppose that you find an iris flower that might either be a Setosa, versicolor or virginica. To determine its species, you measure the sepal length and width and the petal length and width in centimeters. You then plug in the measurements in the equation and do the math. We see that the discriminant score, -3.1, is located between the two cutoff lines. The model therefore predicts that this iris flower is a versicolor. Remember that we previously used LDA to classify bacterial and viral infections. If you also have data on parasitic infections, as well as on other clinical variables, such as the PCT concentration in blood, then we could combine the variables and use the discriminant function to predict if someone has a viral, bacterial, or parasitic infection. Since these clinical variables can be measured within just an hour, an early decision can be made about how to treat the patients long before the actual type of infection can be determined, which usually takes days to confirm. However, remember that we first need to validate our model before we use it for predictions. We also need to consider the prevalence in the population, as we discussed in the lecture about the positive and negative predictive values. Note that when we have three groups, there will be two useful discriminant functions, and if we have four groups, there will be three useful discriminant functions, and so on. However, the first discriminant function generates the best separation, whereas the other discriminant functions do not usually improve the separation that much, which is the reason why just one discriminant function is commonly used, because it simplifies the predictions. This was the end of this lecture about using LDA as a classifier. Thanks for watching.